Hello everyone, let's analyze. So today we're going to talk about Cauchy sequences. Before I tell you precisely what they are, let's recall our quest for the square root of 2. We know it exists, and we know that if we square it, we arrive at 2. But what number is it exactly? Or even approximately? Suppose in an effort to approximate it, we built a convergent sequence with the square root of 2 as its limit. But how can we show that the difference of our sequence entry minus the square root of 2 is less than epsilon if we don't know exactly what the square root of 2 is, only what it does when squared? Now, soon, because we know what it does when squared and we know what 2 is, we'll learn that the square root or the squaring process is a continuous process, and we'll be able to use the machinery of continuity to prove directly that a sequence converges to the square root of 2. But for now, let's consider how could we build a sequence that must squeeze in to the square root of 2. Well, let's see if we can do it. So let's build a sequence that begins with 1 and 2, because we know that the square root of 2 has to be between 1 and 2. And just for the sake of illustration, the square root of 2 is there as the red dot. Now, how do I know that the square root of 2 has to be between 1 and 2? Well, because 1 squared is less than 2 and 2 squared is greater than 2. And because squaring is a strictly monotonically increasing function for positive values, that implies that 1 is less than the square root of 2 and 2 is greater than the square root of 2. Right? 1's not enough and 2 is too much. So the idea is to take those two numbers and just cut it in half and add that number to our sequence. So now we have the sequence 1, 2, 3 halves. And 3 halves is closer, but it's still too much, because 3 halves squared is 9 quarters. So that's 2 1/4, and that's of course greater than 2. So 3 halves is closer, but it's still too much. So let's zoom into that interval and cut it in half again. What about 5 quarters? Well, 5 quarters is not enough, right? 5 quarters squared is less than 2. So that means the square root of 2 has to be between 5 quarters and 3 halves. So while we haven't yet arrived at the square root of 2, we're closer. In fact, we're within a quarter interval. So let's zoom in and cut that sequence of two numbers in half, so we get 11/8. Now, 11/8 is still not enough, because 11/8 squared is less than 2. Now, the square root of 2 lies between 11/8 and 3 halves, and that gap is 1/8. So we're getting closer and closer to the square root of 2. So we'll zoom in again. We'll take the halfway point, 23/16. We square it, that's too much. So the square root of 2 is between 11/8 and 23/16. The difference of those two being 1/16. Right? So we're at most 1/16 away from the square root of 2. And notice, because we keep cutting numbers in half, the numbers in our sequence are getting closer and closer to each other. So 23/16 is too much. Let's zoom in. Let's cut in half again. We get 45/32. If I square that, I get something less than 2, so not enough. So we zoom in, cut it in half. 91/64 is too much because if I square that, I get something greater than 2. So we zoom in and cut it in half. Again, 181 over 128. That's pretty close, actually. But it's not the square root of 2. In fact, it's less than the square root of 2 because if I square it, I get something less than 2. So again, we're going to zoom in, cut it in half. That's too much. We zoom in again, cut it in half. That's too much. We zoom in again, cut it in half. Now, we can keep going forever, and in fact, the sequence does in fact go forever according to this rule. While it might be hard at this point to directly prove that my sequence converges to the square root of 2, what is clear is that the entries in the sequence certainly do get closer and closer to each other. So there we have the sequence that we just built. We have a rule for creating new entries in the sequence, so we can take the sequence forever. We can see visually that, of course, this sequence must, according to the rules we gave, it must converge to the square root of 2. But what's also clear is that the entries in the sequence certainly do get closer and closer to each other because the distance between consecutive sequence entries cut in half at every step I take by the way I construct them. So now we can give the definition of a Cauchy sequence. A sequence is Cauchy if the sequence entries grow and remain arbitrarily close to each other. Stated more technically, a sequence is Cauchy if and only if for all epsilon greater than 0. Right? The for all positive epsilon, that's the arbitrarily criteria. There exists a natural number n for which the following is true. If both little m and little n are greater than or equal to big N, then the difference between such sequence entries in absolute value is less than epsilon. So in this case, we don't need to know what the limit is, or really, at this point, know if there is a limit. All we need to show that a sequence is Cauchy is to show that the sequence entries get as close to each other and remain as close to each other as anyone might like. In other words, they have to be within and remain within epsilon of each other forever once they get to a certain point, and that certain point is the big N. So an example of a Cauchy sequence would be the one we just built. Since the first difference is 1, which is 2 to the 0, the second difference, in other words, x3 minus x2, that's half. x4 minus x3, that's a quarter. x5 minus x4, again, in absolute value, of course, 1/8. And we can keep going forever because I'm taking a distance of 1 and cutting it in half every single step I take. The difference between consecutive sequence entries has to be 1 over 2 to the big N minus 1 if I'm taking the distance between x big N plus 1 and xn. Now, I know that 2 consecutive entries have a distance of 1 over 2 to the n minus 1. But what about every sequence entry after that? Well, because every sequence entry after that has to fall within a 1 over 2 to the n minus 1 distance, for every little m and little n greater than or equal to big N, the difference remains less than or equal to 1 over 2 to the n minus 1. And notice that we've almost satisfied the definition of Cauchy. All that really remains is to show that 1 over 2 to the n minus 1 can be made arbitrarily small. Of course, 2 to a power can be made arbitrarily large, and 1 over that can be made arbitrarily small, but let's show that rigorously. We know that if little m and little n are greater than or equal to big N, then the distance between xm minus xn is less than or equal to 1 over 2 to the n minus 1. Now, let epsilon be positive. That's, of course, how these proofs begin. Let epsilon be positive. Of course, we don't know anything past that about epsilon because it's important that epsilon is arbitrary. Now, since the logarithm is a strictly increasing function for positive arguments, 1 over 2 to the n minus 1, which is of course the same as 2 to the negative n minus 1, is less than epsilon if and only if the log base 2 of 2 to the negative n minus 1 is less than the log base 2 of epsilon. Now, I'm using the base 2 logarithm because, well, I've got a base 2. And what is the base 2 log of 2 to the negative n minus 1? Well, remember what the base 2 log is asking. It's asking what power of 2 equals 2 to the power of negative n minus 1. Well, of course, negative n minus 1. 2 to the negative n minus 1 equals 2 to the negative n minus 1. Which is, of course, 1 minus n. So then this inequality here is equivalent to this inequality here. Of course, I can add n to both sides and subtract the log of epsilon from both sides. And I get 1 minus the base 2 log of epsilon is less than n. Now notice what I did here. I took the inequality I needed and I solved for n because I need to show an n exists. And does such an n exist? Does such an n exist that's greater than this? Of course. Epsilon is a given number. The log base 2 of epsilon is some number, and 1 minus it is some number. Well, there's always a natural number greater than some number because the naturals are unbounded. So let n be a natural number that satisfies this inequality, and of course it has to exist. Now suppose that little n and little m are greater than or equal to this big N. Well, we know what happens if little n and little m are greater than or equal to big N. Right? We concluded that in the previous slide, but we wrote it up here at the top. So we know that this is true. Right? We need to show that this, that is this, is less than epsilon. If this is true, and this is true. Now, remember, n is a natural number satisfying this inequality, so we'll begin there. Now, essentially, if each of these steps can be reversed, then we can say we're done, but we didn't do each step as an if and only if. If we did, logically we'll be done. But again, let's just begin with n greater than this, and we'll logically move forward step by step. So from that I can subtract 1 from each side. I can take the negative of both sides, which means I need to flip the inequality. And then I can raise 2 to both sides. I can do that because 2 to the x is strictly increasing. So if my arguments, if one argument is less than one argument, then 2 to that argument is less than 2 to that argument. Now, of course, 2 to the log 2 of epsilon is epsilon, because log 2 of epsilon means 2 to what power is epsilon? Well, if I raise 2 to that power, I must get epsilon. Which concludes that the absolute value of xm minus xn is less than epsilon, because their difference is less than 2 to the negative n minus 1, and 2 to the negative n minus 1 is less than epsilon. So long as little n and little m are greater than or equal to big N, which exist, right? A natural number exists that satisfies this. So we're done. We've just proven that the sequence must be Cauchy. But is it convergent? Again, we saw it in action. We saw it got closer and closer and closer to the square root of 2. We saw that the distance to the square root of 2 must be bounded by 1 over 2 to the n minus 1. But we didn't just now prove that it converges to the square root of 2. What we did is we proved that it was Cauchy. So is a Cauchy sequence necessarily convergent? Or is a convergent sequence necessarily Cauchy? We're going to answer one of those questions right now. Every convergent sequence is a Cauchy sequence. So convergent implies Cauchy. Of course, you might be asking, well, doesn't Cauchy involve convergent? Well, you have to stay tuned for that. So let's prove this theorem. Let's prove that every convergent sequence is Cauchy. And the idea is that since the entries of the sequence that is convergent get arbitrarily close to a limit, let's call it A, then they get arbitrarily close to each other. At most, they're twice as far away from each other as they are to A. Right? A convergent sequence gets arbitrarily close to A. So of course, one might be epsilon to the left of A and one might be epsilon to the right of A, which means these two sequence entries are about 2 epsilon from each other. So let's prove this. Suppose the sequence AN converges to A, and as always, let epsilon be positive. Our goal is to show that a natural number exists for which little m and little n greater than or equal to big N implies that the sequence entries in distance is less than epsilon. Now, note that epsilon over 2 is positive, so by definition of convergence, because remember, we're supposing that AN converges, which means I can suppose that the definition of convergence is true. There exists a natural number such that if little n is greater than or equal to that natural number, the distance between AN and the limit is less than epsilon over 2. Now, this is what we know. This is our goal. Our goal is here. We're here. We got to go from here to here. So let's start with this expression and let's add 0 to this expression, but with style and verb. So AN minus AM, and again, we want to build eventually to get this to be less than epsilon using what we know here. So here's where we add 0 by adding negative A and A. We group AN minus A and we group A minus AM. Of course, we didn't really do anything other than emphasize that we're going to group this and group this. And then using the triangle inequality, we can say this expression is less than or equal to an minus a and a minus am. Now, so long as n, this n here, is greater than or equal to big N, then this is true, right? And this is true for any integer greater than or equal to this big N. So if m is one of those integers greater than or equal to big N, in addition to this integer being greater than or equal to big N, then I get this result for both of these terms. So I get that this distance, an minus am, which is less than or equal to the sum of these things, but each of these are less than epsilon over 2. So I have epsilon over 2 plus epsilon over 2. And 2/2 of an epsilon is a full epsilon. And we have our result. Right, we're done. We've shown now that the sequence is Cauchy. Because if we look at the terms in red, we have exactly the definition of Cauchy. Let epsilon be positive. There exists a natural number such that if little n is greater than or equal to big N and little m is greater than or equal to big N, then the distance between my sequence entries an and am is less than epsilon. But we still haven't shown that our original sequence converges to the square root of 2 rigorously, even if it's clear visually. We've only shown that that sequence is Cauchy. And we have not shown that a Cauchy sequence must be convergent. We've shown that a convergent sequence must be Cauchy. So, are all Cauchy sequences convergent? Is the idea of convergence and Cauchy equivalent notions? Well, to the answer to that question, you'll have to stay tuned. That's all for today.